Good afternoon, everybody. Good afternoon. So, yesterday I shared the problems on different process scheduling algorithms. I hope all of you received it, and I also sent the submission date, that is, you should submit it on or before 20th of April. Through the Google Classroom link. Afterwards, I'll share the Google Classroom password. Okay, and today morning also I shared the module 2 questions and I sent it to Madhushri. I hope she shared in the group. Is it so? Whether she shared the questions in the group or not? Share? Tell me yes or no. At least send the message. Whether you received the module 2 questions or not. Received? Okay. Uh, so now we will start the comparison of different scheduling algorithms. All of you can see that I shared the slide here. The comparison of different scheduling algorithms. So far you have studied a different scheduling algorithms such as FCFS, first come first serve algorithm, round robin algorithm, priority algorithm, shortest job first algorithm, and also multi-level queues. In multi-level queues you have studied multi-level queues with feedback and without feedback, right? Those two types. So here the comparison is given depending on what type of policy, whether it is a preemptive or the preemptive policy, and whether it is a whether this algorithm is used in the interactive processors or in the batch processors, and what are the advantages of each algorithm and also the disadvantages of each algorithm. I will share this slide afterwards. You can go through that. So simple one. So here just we are deciding whether it's a non-preemptive policy or the preemptive policy, and whether it is used in the batch processors or in the interactive processors or not. Then what are the advantages and disadvantages? You can go through that, and if in the exam they ask, you have to compare and you have to give the answer like this. List out different types of algorithms and what about the policy advantages and the disadvantages, right? If any doubt in this algorithms you can ask, otherwise I'll go to the next topic, that is the last topic of this chapter, that is thread scheduling. Any doubt in this? Or so far you have gone through the different scheduling algorithms, right? You have studied. If any doubt in any of the algorithm, you can please ask. Otherwise I'll move on to the last topic of the chapter, that is thread scheduling. Any doubt in this? Then okay, I'll move on to the next topic, that is thread scheduling. So in the previous chapters, that is in the fourth chapter, you already studied what are threads and what are different types of threads, right? There are two types of threads, user threads and also the kernel threads, that you already studied, right? And also I explained what are user threads and what are kernel threads, and when we are using user threads and when we are using the kernel threads, right? Any doubt in this, in the threads and all? No? Then we'll move on to the thread scheduling, right? I'll share that slide also, thread scheduling. So as I said, you already studied the user level threads and the kernel level threads, and so user level threads are for running the user processes, whereas the kernel level threads for running the kernel programs, where kernel threads are supported by the operating system, whereas the user threads are managed by the thread library, right? User threads are managed by the thread library. To then as all of you know that to run on a CPU, user level threads must be mapped to the associated kernel threads. While discussing the different levels of threads, I explained, right? Different threading models, one to one, one to many, many to many, and many to one, that you have studied, right? So while discussing that, I said that each user level thread should be mapped to the kernel level thread, that I already explained, right? Right. So while uh, I'll share that slide, please wait. Okay, so as I said, user level threads are ultimately mapped to the kernel level threads. Then how the mapping takes place? The mapping takes place through the lightweight process. So that also I explained in the 4th chapter, right? With the help of the lightweight process, each user thread is mapped into the kernel level thread. So there is an indirect mapping there. So each user level thread is mapped to the kernel thread through the lightweight process. So here in this section you are going to study about what are the issues involved in mapping the user level threads to the kernel level threads, or the issues involved in user level threads and the kernel level threads. So basically we are considering the issues related to the process contention scope and the system contention scope. I think understood what are user threads, kernel threads, and how the mapping takes place, right? Through the lightweight process, user level thread is mapped into the kernel level thread. So next we'll see what are the contention scope. That's a slide I here shared. What is a contention scope? Then you'll see the process contention scope and the system contention scope. So here then how we are distinguishing the user level the kernel level threads, that you already know, right? So one distinction between user level threads and kernel level thread lies in how they are scheduled, means how we are scheduling the user level threads and how we are scheduling the kernel level threads through the lightweight process. So that is the difference, right? So the difference between the user level thread and the kernel level thread lies in how they are scheduled, means how the user level threads and kernel level threads are scheduled, that we'll see now. So you already studied that we have many to one model and the many to many thread models. So what are many to one model? So we have many user level threads and one kernel level thread, then the mapping takes place. But in the many to many, what happens? We have many user threads as well as many kernel threads are there, right? So then as I said, user level threads are mapped into the kernel level threads through the lightweight process. But who is responsible for that? So here the thread library schedules user level threads to run on a available lightweight process. Understood? Here to map the user level threads onto the kernel level threads, we are using the lightweight process. Then how to schedule that, or how to map the user level threads to the lightweight process? Here the thread library schedules the user level threads to run on the available lightweight process, and that scheme is called as process contention scope. Here the thread library, just a minute, the thread library scheduler schedules user level threads to run on available lightweight process, and that method is called as a process contention scope. Understood? So here we have the user level threads, then that should be mapped to the kernel level threads. But how the mapping takes place? Through the lightweight process, right? So here the thread library schedules the user level threads to run on an available lightweight process, and that method or that scheme is called as the process contention scope. Here, because in the user level we have once the process is created, for each process we have many threads available, right? So many threads available for each process. Then the computation takes place among those threads created for a the particular process. So suppose consider that for process P1, if you have created 10 threads, all threads are the user threads, then those threads should be mapped to the kernel thread. So then who is responsible for mapping? The thread library schedule, or thread library is responsible for mapping those user level threads to the kernel level threads through the LWP. So then the computation takes place among those 10 threads to map into the kernel thread through the LWP. So even though the mapping takes place from the user level thread to the LWP, then we cannot assure that the physical CPU is available for that particular thread. Okay, so only uh, that is once the mapping takes place from user level thread to the lightweight process, then we cannot say that whether that thread is actually running on a CPU or not. So until it gets the kernel level thread, then only it is getting the CPU, otherwise it is not possible. So that is called as the process contention scope. So next one is system contention scope. So to decide which kernel thread to schedule onto a CPU is called as the system contention scope. As I said, user level threads are mapping into the kernel level threads through the LWP. Even though the mapping takes place from the user level thread to the kernel level thread, we cannot assure that thread is running on the CPU. But to decide which kernel thread to schedule onto a CPU, that is called a system contention scope. So once the scheduling takes place through the system contention scope, then it is decided that the mapping has been already taken place, then the thread is running on a particular CPU. So this is about the process contention scope and the system contention scope. This is the major issue exist in the thread scheduling, that is the contention scope. What is process contention scope and system contention scope? So process contention scope exists when we are using the many to one and many threading models, and if there is a one to one mapping, that is one user thread mapping into a one kernel thread, then there is no need of process contention scope. We are directly moving on to the system contention scope, because directly we are mapping the user thread onto the kernel thread. Understood? Any doubt in this process contention scope and the system contention scope? So in the process contention scope, what happens? In the process contention scope, the thread library schedules the user level threads onto the available LWP, whereas in the system contention scope, we are deciding which kernel thread to schedule onto a CPU so that thread will be executed by a CPU. That is called a system contention scope. If the system using the many to one model and many to many model, there we are using the process contention scope. If only the one to one model is used, then we are directly making use of the system contention scope. So the example for one to one model is Windows XP, Solaris 9 and Linux. Such type of operating systems uses the one to one model. So in them they are using the one to one thread model, so directly they are using the system contention scope. Here so in the case of process contention scope, as I said, for each process we have created multiple threads, and each thread is competing each other to get the CPU or to get mapping it into the LWP, right? So here once the threads are created for the process, and each thread will have the priority. So for each thread, priority is assigned by the programmer, and once the priority is allocated or assigned, always the higher priority threads will be executed. If no higher priority threads are available, then lower priority threads are start executing. But during that time, if the higher priority threads comes, then the preemption occurs. And then the low priority threads execution stops, and once again the high priority thread execution starts. So this is called as the preemption, right? So in the process contention scope, since multiple threads are created for each process, hence the preemption occurs. So because for each thread priority is assigned, and always the higher priority threads are allowed to execute first. And if no higher priority processes are there, no higher priority threads are there, then low priority threads are started executing. But during that time, if high priority thread comes, then the preemption occurs, then CPU start executing the high priority threads. So this is about the process contention scope and the system contention scope. Any doubt in this? So next we'll move on to the p-thread scheduling. So in the previous classes you already studied different types of threads, right? P-threads, Java threads and the POSIX thread, right? So here we are highlighting the POSIX we are highlighting the POSIX pthread API that allows the specifying either we are using the process contention scope or the system contention scope during the thread creation, right? So means whenever we are creating the threads for the process, during that time itself we are specifying whether it is the process contention scope or the system contention scope. So for that we are using these two types of scope values, that is pthread scope process and the other one is pthread scope system. So pthread scope process schedules threads using the process contention scope scheduling, whereas the pthread scope system schedules the threads using system contention scope scheduling. So first one is for PCS scheduling and the second one is for SCS scheduling. So while thread creation itself we are specifying whether it is based on the PCS scheduling or it based on the SCS scheduling. So on system implementing the many to many model, then we are using the pthread scope process, that is PCS scheduling, because it is a many to many, means many user level threads are there and also many kernel level threads are there. Then mapping should be takes place between the user level threads and the kernel level threads through the available LWP. Hence whichever the systems are implementing the many to many model, they have to specify the pthread scope process, that is for PCS scheduling, right? Any doubt in this? Okay. Then who is maintaining the lightweight process? As I already explained in the previous chapter that all the lightweight processes are maintained by the thread library, and through the scheduler activations the thread library is maintaining the lightweight process. Understood? So lightweight processes are maintained by the thread library using the scheduler activations. And what is this? A pthread scope system. So this will be used after the pthread scope process, or it is used in the one to one thread model, right? So this scheduling policy will create and bind the lightweight process for each user level thread on the many to many systems. So if the system uses one to one model, directly it is using, but if the system uses the many to many model, then this one, that is pthread scope system scheduling the policy will create and bind the LWP for each user level thread. So when we are using this function, then what is the responsibility of this? It will create and bind the LWP for the each user level process. So what is the main responsibility of the pthread scope system? It creates and binds the LWP with the user level threads. That is the main responsibility or the functionality of pthread scope system. Then the pthread IPC provides, just a minute. The pthread IPC provides these two functions, that is pthread attribute set scope and pthread attribute get scope. So it uses these two settings for getting and setting the scope contention scope policy, because we have two types of contention scope, right? Process contention and system contention scope. So for getting and setting the contention scope, we are using these two functions, that is pthread underscore attr underscore set scope, and second one is for get scope. So these two these two functions are used for getting and setting the contention scope policy. Okay, so you can verify these two functions, right? For these two functions, what are the first parameter and the second parameter? In both the functions, the first parameter contains a pointer to the attribute set for the thread. So this is the pointer to the attribute set for the thread. So here it is the pointer for the attribute set for the thread, and the second parameter, that is scope, in the first case, that is the second parameter in the pthread attribute scope specifies whether it is the PCS or the SES. So here the first two parameters, just a minute, the first two parameters of both the functions are pointing to the, are the consisting of a pointer to the attribute set for the thread, and the second parameter in the first function, that is scope, it specifies whether it is the process contention scope or the system contention scope, right. And in the second function, that is star scope, right, see the difference, in the first case it is directly, it is the scope, and in the second case it is the star scope. So in the first function it indicates whether it is a process contention scope or the system contention scope, but in the second one it contains a pointer to the integer value that is set to the current value of the contention scope. Understood? So clear? See here, in the first function scope it specifies whether it is the process contention scope or the system contention scope, but in the second function it consisting of the pointer, right, it contains a pointer to an integer value. So it contains a pointer to an integer value that is set to the current value of the contention scope. Understood? That is set to the current value of the contention scope. So whether it is a process contention or the system contention, for each one we have the value, and that value is specified by the star scope. Understood? So this is the pointer contains a pointer to an integer value that is set to the current value of the contention scope, right. So how we are specifying the current contention scope? Through the, for we are setting the value for process contention scope and the system contention scope, and that value is specified here, that is the star scope, that is pointing to the integer value that is set to the current value of the contention scope. So this is about the process contention scope and the system contention scope. Any doubt in this? What are the thread scheduling, right? What is a thread scheduling? And next is right. So what is thread scheduling? In that we have user threads and the systems threads, and what is process contention scope and the system contention scope. And the in pthread scheduling we are using pthread scope process and pthread scope systems. They specify whether it is a PCS scheduling or the SES scheduling, and we have two functions, pthread attribute set scope and pthread get scope. They are for setting and getting and setting the contention scope policy. So here both the functions, in the first one they have the containing the pointer to the attribute set for the thread, and second parameter in the first function specify whether it is a PCS or the SES, and in the second case, that is the star scope, it is contains a pointer to the integer value that is pointing to the currently set value for the PCS or the SES. So this is about the thread scheduling, and this completes the chapter process scheduling. So in this chapter you have studied what? So you have studied, in this chapter you have studied what is a process, then different process scheduling algorithms, process scheduling criteria, then the comparison between different process scheduling algorithms, and I also solved the problems for each process scheduling algorithms, and the last one is the thread scheduling. In that you studied what are threads, user threads, kernel threads, and how the mapping takes place through the LWP process, then what is the process contention scope and the system contention scope. So this completes the chapter, and two chapters are completed, and in the next class I am going to start the third module, first chapter of the third module, that is deadlock. There you are going to study what are deadlocks, when the deadlock occurs, then how to detect the deadlock, and then afterwards prevention and avoiding the deadlocks. So there you are going to study different algorithms for deadlock prevention and avoidance. So any doubt in this chapter, that is in the process scheduling chapter, as well as in the previous chapter, that is multi-threading, there you have studied different threads, different threading models, and also the threading issues, right? Any doubt in the second module, because I already shared the questions of the second module. If any doubt you can ask now. If not, I'll close my session, and we'll meet on Saturday. On Saturday I'm going to start the new chapter, that is deadlock, that is the third module I'm going to start.